So hello everyone. Welcome to my report on the James Webb Space Telescope. My name is Shreyas, and let's begin. So in the first, you see the table of content, and so the James Webb Space Telescope, right? So it is an engineering marvel of the 21st century, and it took three nations or three organizations to build it. So first is NASA, then the Canadian Space Agency, and then the European Space Agency as well. So the James Webb can look back in time of about 13.5 billion years old. Okay, it is the most powerful, the most complex instrument ever sent to space by man. Just you know, just with the International Space Station. So in this slide, you see the image of the James Webb. So the primary mirror, the gold-plated mirror, it's a beryllium gold-plated mirror, which is almost 4 times wide, 13 times the area of the Hubble Space Telescope. You can see it on the top right. So the James Webb, it's a 3-mirror anistigmat, which means that light, when it bounces on the primary mirror first, bounces back, and then bounces back again into the primary mirror, which goes inside the sensor. So it basically, the light is bouncing 3 times to go inside the mirror. So these hexagon shaped segments are of 18 numbers. So they have to be aligned perfectly, like literally perfectly. Even if there's like one deviation, everything just it's different. So that's why it's a 3-mirror anistigmatic. And so there are 4 mirrors, but the 4th one is just for stabilization. So the James Webb is on the Lagrange 2 point, the L2. So that's about 15 lakh kilometers away from here, from Earth. So for comparison, the moon, it's only 3,84,000. So it's almost 3 times away than us. So like Hubble, like there was a small error in the mirror. So we had NASA sent people, and then they had to replace the primary mirror. But in this case, we won't be able to go there. That's why it took more than 20 years to completely build, design, send it into space and all. So it's a very important mission for mankind. So in this slide, you can see that why was L2 chosen. It was chosen because the James Webb is primarily an infrared telescope. So infrared, the beauty is that it can pierce to dust, to atoms, not atoms, to dust clouds in space. So there are a lot of them, say from a star formation, nebula and all. So to be a good infrared camera, it has to be at minus 226 degrees Celsius, which is not possible anywhere near Earth. Hubble was just 500 kilometers above the surface. So it was a good temperature. It could radiate its own infrared infrared wavelengths. So over here, they are removing that aspect from the James Webb. So to support this, they have a huge sun shield, which is the size of a badminton or tennis court. That big. It's 4.8 meters. So over here, you can see the first images taken by James Webb. So that's the Carina Nebula, which is 7,200 light years away. On the right, it's the SMAX 0723, which is mind-boggling. It just shows how small we are in the grand canvas of the universe. So it's like you have a 1 rupee coin with you and you're holding it like this. So the eye of the Ashok Chakra, the eye of the lion in the Ashok Chakra, so if you hold it at arm's length, so that small patch of the night sky, this image covers, which is just mind-blowing. So over here you can see the oldest found galaxy also. So the specifications of the James Webb. So the James Webb requires about 1 kilowatt hours according to NASA. So to support this, they have a 2000 watt capable solar array in the James Webb, and it has rechargeable batteries, which are the Sony's 18650 batteries, which work on the carbon cell technology. So there are about 8 series, like parallel series, which contain 44 cells each, bringing the total to about 352 batteries. And the solar array is 20 foot, so provides enough energy. Yeah. So per battery contains about 5.4 watt hours. So the battery component of the James Webb is about 1900 watt hours, which is more than enough to support it on its lifetime. So yeah, now we're going to talk about the components of the James Webb Space Telescope. So the ISIM, so it involves all the science instruments, all the science studies which we are going to do with the help of the James Webb. We're going to do with the integrated science instrument module. So it includes all Webb's science instruments. So it gathers all the light coming from the universe. It goes through it, analyzes it, and gives us beautiful images of the universe. So there are 4 instruments: NIRCam, NIRCep, MARI, and the Near Infrared Imager. So let's talk about them a little bit deeper. So NIRCam, it was built in partnership with Lockheed Martin and University of Arizona. So it's a camera and also helps control this 18 segments in the telescope. It primarily looks from 0.6 microns to 5 microns. Yeah, so the NIRCam will also be able to detect light from the earliest universes. So NIRSpec. So NIRSpec is a spectrograph instrument. So it is used for spectrography, which involves getting the light from away universes and converting it to its respective wavelengths. So with the help of that information, we can study the source from where it came from, the light. So it was built by the European Space Agency and Airbus. So the crazy thing about NIRSpec is that it has tiny windows known as micro shutters. So it has a thickness of about 100 microns by 200 microns, which is about a few bunch of human hair, which is amazing. So these tiny windows can either block light coming, or we can send an electrical charge and open it, so light will go. So if I have a big picture like my picture right now, and if I want to study only my eye, I can do that by just blocking everything else and just letting the image of my eye going through. There are about 250,000 to 3 lakh micro shutters in the NIRSpec. So the near infrared imager. So the near infrared imager has 2 very specific purposes. So the wide spectrography mode, which studies high redshift objects. Now these high redshift objects are those which are very far away from us, millions of light years. So their light has not converted, it's gone into the infrared spectrum. So that's why they became red in color, just like the galaxy we talked about in glass Z13, and single mode. So over here we'll be able to study the atmospheric composition of exoplanets. So as they go towards their sun, so if this is the sun and this is it goes like this into eclipse, and then the light coming from the host star, the rays gets absorbed, but some goes through. So they'll be the James Webb will be able to study the light the wavelengths which are going through and determine the composition of that atmosphere of the exoplanet. So in the next slide, I'll just show it to you. Yeah, so over here you can see the composition of WASP 96b, which is 1200 light years away from us, and it's about 80% larger than Jupiter. So you can know that there's some water in the atmosphere. Yeah, there's a lot of water in the atmosphere. So our fourth instrument is NIRCam. NIRCam is an instrument. So while other instruments just work from zero point 0.6 microns, which is just the edge of what we can see moving into the infrared spectrum, to 5 microns, which is infrared spectrum. So this picks up from where they leave, which is 5 micron, to 28.5 microns, which is well deep into the infrared spectrum. So to help support this process, we have to make sure that the component itself does not radiate heat, which can emit infrared wavelengths. So it has to work at a bone chilling minus 226 degrees Celsius, which is just 7 degrees above absolute zero. Absolute zero is at a temperature at which even atoms stop working. So it is very sensitive, Mary. It can see faint redshifted objects as well in the night sky. So you might ask, what is the difference between Mary and Neris's wide spectroscopy mode? So Mary's wavelength is way ahead of Neris's wavelength, which is the near infrared imager. So Mary can cut through more dust, more clouds, and see star birth, for example, which is fascinating to study about star birth. So while the four instruments, the amount of energy individually they consume is kept classified, the whole instrument, the ISIM, with the guidance sensors, so all four instruments including the guidance sensors consume about 740 watts of power. Yeah, so now we are going to talk about the safety systems of the James Webb. So the safety systems are designed by the best engineers, best of the best across the world. So it can course correct if it's on a collision course. It has 3 rolling, like a wheel in the main component beneath the sun shield. So if it rotates in a certain direction, it can turn the whole telescope in any direction it wants. So to prevent solar radiation to heat up the components, there are 5-layer sun shield, as I told, size of a tennis court. So the crazy thing is the difference between the temperatures at the side facing the sun and this part facing the telescope is about 315 degrees Celsius, which is mind-blowing. So energy conversions. So the photons as energies coming from faraway galaxies are converted into wavelengths, which help us understand them by the help of diffraction grating. And obviously solar energy is converted into electrical energy. So bandwidth of the transformers, so how fast it can transmit signals back to us. So the S band up is about 16 kilobits per second. The S band down is about 40 kilobits per second, and the Ka band down it'll go up to 28 megabytes per second. So the advantage of James Webb Space Telescope. So it helps us understand the universe in such a great way that we as humans can trace back so much time that we can get to know about how our solar system came about, how we came into existence. So that's very important as a species for us to do. So ground-based telescopes. So JWST is in space, so there's no hindrance from the Earth atmosphere. While ground-based telescope, no matter how powerful they are, they'll have to look through the atmosphere, which which might contain satellites, not in the atmosphere, but around the Earth. It might contain satellites going through which might disturb the process. So in conclusion, I have to say that as humans, we are explorers. From the discovery of fire to Columbus's voyage into the sea, and now into the unknown. The space is just filled with so much mysteries that it's fascinating to know that there are billions of planets alone in the Milky Way, which are in the habitable zone, which might contain life. So I just want to end this by saying, as a species, our future is in amongst the stars. Thank you.